In fewer than 20,000 dao, the Permian extinction wiped out 96% of Earth's life. However, no known natural process can destroy something so quickly or completely. We believe we are Earth's first sentient species, but what if we are mistaken? What if powerful civilizations rose and perished millions of years before humans appeared, leaving only faint remains in rocks and ice? We're preparing to investigate carbon signatures that do not fit natural cycles, extinction patterns that are too well coordinated for chance, as well as geological evidence indicating that intelligence may have existed before. Like and subscribe, because this investigation calls into question some of our most fundamental ideas about life on Earth. Prepare yourselves. We begin in the heart of Africa, amid tons of rock and 2 billion years of stillness. Scientists discovered something that shouldn't exist. AE had somehow managed to arrange natural uranium, self-created ideal nuclear reactors, complete with meltdown prevention measures and waste disposal systems that contained radiation for millennia. These were not rudimentary experiments. They were sophisticated power plants that ran smoothly long before the first fish developed legs. The uranium deposits in Gabon show that uranium-235 was concentrated in a reactor into critical masses, then controlled its own reactions with groundwater as a coolant. Consider it a campfire that constantly adjusts its fuel supply and never burns out of control. However, campfires do not necessitate complex physics and engineering understanding, which humanity has only recently learned. 50 years ago, each reactor produced approximately 100 kilowatts. Power ran for hundreds of thousands of years before safely shutting down. The waste products remained exactly where they were put, protected in natural clay barriers that prevented contamination from spreading to scientists. Isotope ratios identified at the sites match those of modern nuclear waste, indicating that these were not random chemical processes. This revelation is particularly disturbing because natural uranium ore includes less precision. Less than 1% of the fissile, uranium-235, is necessary for sustained nuclear reactions. However, concentrations at Oklahoma approach the exact 3% threshold required for criticality. The likelihood of this occurring randomly across numerous places is mathematically insignificant. Some geologists believe these formations are the product of unusual geological conditions that no longer occur on Earth. The ancient environment had varying oxygen levels, and slower-running groundwater may have concentrated uranium over millions of years. However, this explanation necessitates an incredible chain of coincidences that occurred concurrently across 17 different reactor locations. The reactors were active during the Earth's major oxidation event, when cyanobacteria pushed oxygen into the atmosphere and caused the first mass extinction. Ocean chemistry and atmospheric composition shifted dramatically over this time period. Could some ancient creatures have evolved nuclear technology as their environment changed around them? Could they have built these reactors to power underground facilities while the surface was rendered uninhabitable? We locate no artifacts or tools. There are no apparent signs of intelligence, but the lack of evidence becomes less significant when you consider the timescales involved. Even the most complex civilization would be almost completely erased after 2 billion years of erosion, tectonic activity, and geological recycling. Metal corrodes, concrete crumbles, and organic materials disappear entirely. Nonetheless, radioactive waste is trapped in rock formations. Like an atom-based message, isotope signals reveal a history of controlled fission, precision engineering, and contained disposal. They reflect technologies that humanity is striving to accomplish. Even now, if these reactors were developed by intellect rather than accident, we face a troubling prospect. We may not be the first species on Earth to find nuclear power, and even if we are not the first. What happened to those who came before us? The solution may be found in the rocks themselves, inscribed in the language of extinct atoms and forgotten elements. A cosmic rock 66 million years ago wiped off the dinosaurs in minutes. But what if certain dinosaurs had already established cities, mastered agriculture, and began influencing their surroundings before the asteroid struck. The Saurian theory proposes advanced reptilian civilizations could have existed for millions of years without leaving any marks that we would recognize today. Dr. Gavin Schmidt, a NASA climate scientist, created this thought experiment to demonstrate how difficult discovering ancient civilizations is. He named it after the intelligence reptiles in Dr. Whoa! But the science behind it is quite serious. How would we know that an industrial society existed on Earth 50 million years ago? Consider the immense advantages dinosaurs enjoyed over early mammals. Triceratops had greater brains than modern elephants and formed intricate social organizations. Velociraptors displayed advanced pack hunting methods that needed communication and preparation. Some species, such as the Oosa, developed to huge sizes while eating herbivorous diets, implying that they had addressed large-scale agricultural challenges. Dinosaurs dominated the Earth for more than a century, according to the fossil record. 60 million years. That is 800 times longer than current people have lived during this huge period. Countless species have evolved, adapted, and developed more complicated behaviors. Some created complex nests, others covered thousands of miles. In coordinated migrations, many showed intelligence that might theoretically enable technological development, but uncovering evidence of dinosaur cities is extremely impossible. Fossilization necessitates extremely specialized circumstances, preserving only minuscule percentages of past life. Most dinosaur fossils are from creatures that died near water and were immediately buried in sediment. These preservation conditions are rarely seen in urban environments, rural districts, or manufacturing centers. Even more troublesome is the recycling of the Earth's geology. Tectonic plates constantly shift, subducting ancient ocean floor into the mantle and forming new crust at spreading centers. The oldest ocean floor on Earth is only around 200 million years old. Any proof of coastal civilizations are systematically destroyed and recycled into molten rock and continental surfaces. Surface features fare marginally better, but erosion, weathering, and sedimentation eventually bury or obliterate them. Mountain ranges rise and fall, rivers alter course, and glaciers erode entire landscapes. The Appalachian Mountains were once taller than the Himalayas, but hundreds of millions of years of erosion reduced them to gentle hills. What about technology that could withstand these processes? Modern materials, refined metals and concrete, like plastics, will degrade or become unrecognizable in millions of years. Even radioactive waste from nuclear power plants would degrade beyond detection in the timescales under consideration. However, some signatures may endure in the geological record. Large-scale mining operations may leave different mineral distributions in rock strata. Industrial contamination may cause anomalous chemical concentrations in sedimentary deposits. Mass agriculture may affect soil compositions in ways that fossilize over time. The absence of these indicators does not indicate that dinosaur civilizations never existed. It could simply be that we don't know where or what to look for, yet dinosaurs did develop technological societies. Their tragedy teaches a grim lesson about the fragility of even the most accomplished civilizations. Imagine an entire technological civilization vanished from the Earth's surface. What traces would remain after 100 million years? The answer is both, everything and nothing, depending on where you look and what you consider proof of intelligence. Begin with the most obvious signs of human civilization. Towns, roads, and buildings would be the first to disappear. Even the most enormous concrete constructions would disintegrate into unrecognizable debris within a few million years. Steel rusts fully in wet areas in centuries, as does aluminum. Corrodes more slowly but eventually fades over geological timescales. Glass breaks down into sand. Plastics break down into molecular bits, and even nuclear waste becomes invisible as radioactive isotopes decay. However, some signatures are startling. Persistent, large-scale mining operations produce distinctive geological characteristics known as anthropogenic deposits. Strip mining, copper mining, and coal mining all create scars in rock formations that can last for tens of millions of years. Underground mines also collapse and fill with sediment in patterns that deviate significantly from natural cave systems. Industrial agriculture may leave the longest-lasting imprints, although intensive farming depletes soil of certain elements while increasing others through fertilizers. These chemical changes are integrated into sedimentary rocks as soil layers become stone over millions of years. A society based on agriculture. Thousands of years can leave diverse chemical traces across multiple geological strata. Urban heat islands are another potential indicator. Large cities boost local temperatures by several degrees above those of the surrounding countryside. This warming alters local weather patterns, plant development, and seasonal cycles, all of which influence sediment deposition. Ancient cities may have left heat traces embedded in rock layers, much like fossils. Mass extinctions may provide the most persistent evidence, as measured by temperature data. Human activity is currently promoting species extinction at a rate that is approximately 1,000 times higher than the natural background extinction rates. This leaves a distinct imprint in the fossil record, as diversified ecosystems collapse abruptly and never recover their original complexity. Any advanced society is expected to generate similar ecological upheavals, which leave gaps in the fossil record. Carbon isotope ratios reveal even more subtle signals. Burning fossil fuels emits carbon with different isotopic fingerprints that differ from carbon cycled by living organisms. Industrial civilizations would use large amounts of this old carbon into the atmosphere, resulting in measurable carbon dioxide increases that have been preserved in ice cores, marine sediments, and fossil plant tissues. Consider how metal processing can leave traces. Smelting ores concentrates heavy metals such as lead, mercury, and cadmium in ways that would not occur naturally. Ancient smelting sites may still be visible as anomalous metal concentrations in soil. Chemical fingerprints may remain on rock layers even after the original processing facilities have eroded away. Satellite archaeology highlights how small clues can be revealed with the correct tools buried. Roman roads appear in aerial images because they induce minor changes in soil chemistry that influence plant growth. Ancient building foundations, they appear as geometric patterns in wheat fields. Thermal imaging detects minuscule fluctuations in ground temperature, revealing archaeological sites. But herein lays the critical issue. We are looking for proof of something we do not understand, using approaches meant to discover things that we already know exist. Ancient civilizations may have used technology, materials, and energy sources that were fundamentally different from our current industrial ways. Their traces may be hidden in plain sight, written in a language we have not yet learned to read. Deep in Antarctic ice cores, scientists discovered carbon isotope ratios that tell incredible stories. The statistics do not match any known natural process. They emerge regularly across several drilling sites and throughout thousands of years. These chemical signatures indicate huge releases of ancient carbon into the atmosphere at IRAs when no natural mechanism could explain such occurrences. Carbon exists in two stable forms that function as geological fingerprints. Carbon-12 accounts for the majority of natural carbon, with carbon-13 appearing in lesser but substantial proportions. Different processes produce distinct ratios of these isotopes. Plants want lighter carbon-12 during photosynthesis, which produces predictable patterns in organic materials. Volcanic eruptions emit carbon in varying ratios. Depending on the source of the magma, however, the unexplained signatures do not fit into either category. They display carbon isotope ratios that are compatible with significant fossil fuel burning at irregular intervals. Over the last few 100,000 years, these surges occur unexpectedly in the ice record, last for ages or millennia, and then vanish just as quickly. The timing does not make sense from a natural standpoint. Ice ages and interglacial eras have predictable cycles, driven by variations in the Earth's orbit. Natural climate variations cause progressive adjustments in atmospheric chemistry. Massive releases of ancient carbon volcanic activity can pump vast amounts of CO2 into the atmosphere, but only gradually. However, volcanic carbon's isotope ratios diverge significantly from the mystery indications. Changes in ocean circulation can help to mobilize carbon trapped in deep water and marine sediments. During abrupt climate shifts, warmer waters release dissolved carbon dioxide and methane from undersea deposits. However, these natural carbon releases have distinct isotope patterns that do not match the aberrant measurements from ice cores. Some scholars believe the fingerprints are the result of huge forest fires or peat bog combustion during exceptionally dry climate periods. Burning organic matter produces carbon dioxide with the appropriate isotope ratios, but the scale required to cause the observed atmospheric changes would necessitate the simultaneous consumption of an entire continent's worth of vegetation. Even more puzzling, carbon increases frequently coincide with other atmospheric abnormalities. Methane concentrations rise during the same time periods, although methane isotope ratios indicate industries. Rather than biological sources, trace metals such as lead and copper are found in higher concentrations during these occurrences. Despite the fact that there are no known natural processes capable of mobilizing both greenhouse gases and heavy metals at the same time, the geographical dispersion adds to the enigma. Greenland ice cores exhibit similar abnormal carbon fingerprints. This global synchronization, which occurred at the same time as the events in Antarctica, shows that whatever triggered these events did so on a global scale. Natural mechanisms that affect both poles at the same time are confined to genuinely catastrophic occurrences such as huge volcanic eruptions or asteroid impacts, but neither theory is consistent with chemical evidence. Marine sediment cores collected from ocean floors throughout the world provide independent corroboration. Deep water drilling exposes layers with carbon anomalies that appear at the same time as the ice core traces. Ocean sediments maintain many aspects of atmospheric chemistry, making it extremely hard for errors to produce identical false signals across multiple types of geological records. Perhaps most disturbingly, several of these carbon signature occurrences coincide with catastrophic extinction events in fossil record species. Diversity declines considerably during eras when unusual carbon ratios arise in ice and sediment. Recovery takes thousands of years, implying that whatever caused the carbon emissions also precipitated ecological catastrophe. If these signs indicate unknown natural processes, they tell something new about the Earth's climate system otherwise. They represent something altogether different. We're looking at evidence of industrial-scale operations that happened long before humans existed. Either hypothesis necessitates a comprehensive rethinking of what we believe we know about Earth's history. Hidden in rocks on 6 continents, uranium isotopes provide evidence that defies what we know about natural radioactive decay. These atomic fingerprints emerge in strata dating back millions of years, revealing enrichment patterns that necessitate advanced separation technologies. Humans only emerged during the atomic era, yet the rocks that house them formed when dinosaurs dominated the Earth. Natural uranium has 99.3% uranium-238 and less than 1% uranium-235. This ratio is fixed throughout the solar system because both isotopes decay at predictable rates that have not changed in billions of years. Nuclear engineers can calculate how much uranium-235 should be present in any sample based on its age and geological background. However, samples from several mining sites reveal uranium-235 amounts that surpass theoretical limits. Some rocks have enrichment levels of 15 to 20%, which could only be the result of artificial isotope separations. Natural processes do not concentrate when using gas centrifuges or electromagnetic technologies. Uranium-235. Without additionally concentrating uranium-238 in predictable amounts, the enriched samples do not cluster at known nuclear facilities or weapons testing sites. They are found in old rock formations, prehistoric riverbeds, and geological layers. Carbon dating and radiometric study reveal that the host rocks formed millions of years before human civilization. The enriched uranium is frequently found alongside other isotopic abnormalities. This suggests that regulated nuclear processes, plutonium, and isotopes that do not exist naturally appear in trace levels in the same rock samples. Neptune ratios show artificial transmutation reactions involving fission product isotopes such as cesium. Strontium concentrations and distributions are consistent with nuclear reactor waste. Independent laboratories validated these findings using various analytical techniques. Mass spectrometry, neutron activation analysis, and gamma-ray spectroscopy all provide consistent results. Sample contamination has been eliminated through a meticulous chain of custody, protocols, and study of nearby unaffected rock. The geographical distribution is vast, with a variety of geological environments. Enriched uranium traces can be found in Canadian shield formations, Australian desert deposits, Siberian permafrost, and African craters. The common factor is neither location nor geological age. However, proximity to places with unique mineral compositions or indications of historic hydrothermal activity. Some samples clearly reveal indications of long-term controlled nuclear reactions. Isotope ratios suggest continuous fission processes that produce consistent power while avoiding runaway reactions. Neutron flux patterns maintained in surrounding minerals propose reactor configurations that enhance fuel efficiency while minimizing waste output. The reactor signatures differ significantly from those of natural Euler reactors in Africa, whereas Oklahoma provides evidence of water-moderated reactions that began and halted depending on groundwater availability. These mysterious reactors appear to have had sophisticated control methods. Isotope distributions point to active fuel management, precision neutron control, and planned waste processing. Critics contend that unknown geological processes may concentrate uranium isotopes by selective leaching, transport, and deposition. Certain minerals preferentially absorb uranium-235 during production at specified temperatures and pressures. Hydrothermal solutions may selectively dissolve and transport various uranium isotopes based on tiny chemical variations. However, proposed natural explanations necessitate the simultaneous occurrence of numerous implausible situations in many geographic places. The statistical probability of natural isotope fractionation. When calculated thoroughly, the production of reactor-grade uranium concentrations at dozens of sites becomes vanishingly small. Isotopic data suggests that controlled nuclear technology existed millions of years before humans discovered radioactivity. If validated, these findings indicate civilizations capable of advanced atomic engineering thrived and died long before recorded history began. However, validating such exceptional claims necessitates extraordinary evidence, which may remain forever beyond our grasp. The fossil record reveals 5 big mass extinctions that wiped out the majority of life on Earth. However, deeper analysis reveals that several events occurred at an unnaturally rapid pace. Natural calamities, such as volcano eruptions and asteroid collisions, take time to spread their lethal consequences across the planet. However, certain extinction events destroyed species on multiple continents at the same time, implying that the destruction was coordinated and far exceeded any known natural mechanism. The Permian extinction 250 million years ago wiped out 96% of marine creatures, and 70% of land animals are extinct. Traditional explanations point to massive volcanic eruptions in Siberia that pumped greenhouse gases and toxic chemicals into the atmosphere over hundreds of thousands of years, but recent high-precision dating shows the extinction occurred in less than 20,000 years, possibly as quickly as a few thousand. 20,000 may appear to be a long period, but in geological terms, it is the equivalent of an eye blink. In comparison, human industrial activity has significantly impacted global climate in less than 2 centuries. A natural process that eliminates nearly all life on Earth in 20,000 necessitates energy release rates that far exceed any known geological mechanism. During the late Permian epoch, the Siberian Traps volcanic province erupted massive lava flows. However, a careful investigation of lava chemistry indicates discrepancies with the extinction timeframe. The largest eruptions happened after many species had vanished from the fossil record. The initial volcanic activity was rather small and should not have caused global ecological collapse. What's more intriguing is that the extinction hit diverse environments in coordinated waves that did not match volcanic impact patterns. The deep ocean species died first, followed by shallow marine life. Then we have terrestrial ecosystems. Volcanic gases often impact land habitats before reaching deep ocean waters, reversing the observed extinction order. Carbon isotope fingerprints preserved in rock strata suggest that atmospheric CO2 concentrations increased considerably throughout the extinction period. However, the isotope ratios do not match volcanic carbon sources. They believe that forest fires and soil decomposition cause enormous emissions of organic carbon. Instead of direct volcanic emissions, marine ecosystems are collapsing. Similar anomalies were observed during the conclusion of the Cretaceous extinction 66 million years ago. The asteroid that killed the dinosaurs undoubtedly had enough energy to cause widespread environmental collapse. However, temporal data implies that severe ecosystem changes occurred before the event. Dinosaur diversity had already declined. Marine food webs were collapsing, and atmospheric chemistry was shifting months or years before the space rock arrived. Core samples from the impact crater show numerous layers of shocked minerals and debris that do not match single impact estimates. Some evidence shows that a succession of lesser impacts or explosions occurred before the big asteroid impacted. Alternate possibilities include massive volcanic activity in India. However, the timing does not precisely correspond with the extinction sequence. The last Trias extinction occurred 200 million years ago. The extinction of 76% of marine species allowed dinosaurs to evolve and dominate terrestrial ecosystems. Volcanic activity, climate change, and ocean acidification are some of the proposed causes. However, the rate of species extinction exceeds models of natural environmental change. Ocean chemistry data demonstrate that rapid acidification killed marine species with calcium carbonate shells in thousands, not millions, of years. Volcanic activity produces natural carbon dioxide, which normally takes significantly longer to acidify the ocean. Significantly, the observed chemical alterations point to concentrated acid discharge rather than gradual atmospheric carbon dioxide buildup. Some researchers believe that ancient civilizations may have caused rapid environmental changes through industrial activity, warfare or technological accidents, nuclear weapons testing, large-scale fossil fuel burning, or failed geoengineering projects, which could theoretically result in extinction-level environmental damage within thousands of years. However, such explanations need complex technical civilizations that have existed for millions of years. Prior to human evolution, the fossil record contains no strong indication of intelligence during these ancient periods. However, the absence of evidence becomes less important over geological timeframes, whether natural or manufactured. These extinctions show how swiftly global ecosystems can collapse when pushed past crucial limits. The cycle repeats throughout Earth's history, like a nightmare carved in stone and bones. The Drake equation predicts that millions of intelligent civilizations will exist in our galaxy alone. Despite 70 years of searching, we've found nothing but cosmic static. The absence of foreign signals gave rise to the Big Filter hypothesis. One of the most unsettling hypotheses in modern science proposes that something destroys nearly all intelligent life before it can spread beyond its home planet. The results should be favorable. Our galaxy has approximately 400 billion stars, with new discoveries indicating that most stars have planetary systems. According to conservative estimates, billions of planets have habitable zones with liquid water on their surfaces, despite the fact that intelligent life is extremely rare. The sheer quantity of opportunities should result in detectable civilizations somewhere in our cosmic neighborhood, but the electromagnetic spectrum is strangely quiet. Radio telescopes search millions of frequency channels across thousands of star systems, but detect no man-made signals. Optical searches seek laser pulses or early filter possibilities show that life is extremely unlikely. despite billions of years and innumerable planets. Perhaps Earth is the only place with self-replicating chemistry, successfully emerged from non-living matter. The shift from simple organic molecules to living cells may necessitate such precise conditions that it is unusual, even across geological timescales. Alternatively, the filter may exclude species during the shift from simple to complex life. It took the Earth more than 2 billion years to evolve nucleated cells from bacterial forebears. This massive temporal gap implies that the evolution of biological complexity meets basic constraints that most biospheres never completely overcome. Despite the fact that millions of species have evolved on Earth, intelligence may act as a filter. Over hundreds of millions of years, just one lineage evolved technology capable of spaceflight and radio transmission. The cognitive qualities required for science and engineering may arise so infrequently. Most biospheres never create intelligence-based tools, but late filter situations present more dangerous possibilities. Perhaps intelligence evolves on a regular basis throughout the galaxy, but technological civilizations destroy themselves in order to achieve interstellar expansion capability. Nuclear war, ecological collapse, artificial intelligence, earthquakes, and other technical calamities may pose virtually insurmountable hurdles to emerging species. The time of humanity's emergence makes these considerations more urgent. We developed agriculture, literature, and industrial technology in the last few thousand years, following millions of years of hunter-gatherer survival. This tremendous technological acceleration implies that we may be approaching our own encounter with whatever filter. The majority of intellectual species are eliminated. Current human activities demonstrate potentially catastrophic patterns. Climate change jeopardizes worldwide agriculture systems. The proliferation of nuclear weapons raises the risk of civilization-ending violence. Artificial intelligence development moves quickly, with minimal safety studies. Ecological deterioration wipes out species at a rate comparable to earlier mass extinctions. If the Great Filter is ahead of us, rather than behind us, humanity faces difficulties that have annihilated countless past civilizations. The quiet from space may not reflect the absence of intellect, but rather the graveyard of species that fail to make the leap to sustainable interplanetary existence. Recognizability may be critical to our survival, and successfully getting through whatever evolutionary bottleneck has wiped out our prospective galactic companions. 4 billion years ago, Mars had flowing rivers, enormous oceans, and an atmosphere thick enough to support liquid water on its surface. For millions of years, fresh discoveries have indicated that ancient Mars may have been more favorable to life than early Earth, raising serious questions regarding what kinds of animals or perhaps civilizations could have lived there before the planet died. Multiple Mars rovers and orbital surveys have provided data, mapping the planet's geological history in unparalleled detail. Ancient riverbeds stretch throughout the Martian landscape. Thousands of miles were shaped by river flows that lasted for millions of years. Sedimentary rock strata reveal evidence of lakes and shallow seas that existed during Mars' warm, wet season. Spectroscopic examination demonstrates that clay minerals can only develop in the presence of liquid water over long periods of time. These clay deposits are rich in complex organic compounds and chemical fingerprints associated with life activity. Some formations exhibit layered structures comparable to stromatolites on Earth, which represent some of our planets, early indication of microbial life. However, Mars had an advantage over the early Earth in terms of harboring complex life forms. The planet's decreased size resulted in lesser gravity, making flight easier for any emerging organisms. Reduced atmospheric pressure would have allowed for more effective gas exchange and respiratory systems. The planet's distance from the Sun gave protection against solar flares and radiation that pummeled our worlds. Most intriguingly, Mars appears to have had stable climate conditions for far longer than early Earth. While our planet underwent many snowball Earth episodes and huge volcanic disasters, Mars had relatively mild temperature fluctuations during its habitable history. This stability may have given evolution more time to build complex species, including intellect. The planet's two small moons, Phobos and Deimos, generate distinct tidal patterns that differ significantly from Earth's sole giant moon. These complicated tidal cycles may have offered extra energy sources during early life and produced a variety of biological niches. Recently discovered subsurface water may promote rapid evolution toward intelligence. Ice and possibly liquid water reservoirs indicate that Mars may have remained somewhat habitable long after surface conditions deteriorated. As the planet's atmosphere went into space, underground ecosystems could have provided a safe haven for species. Advanced species may have created underground civilizations. To survive the shifting surface environment, Mars' fall corresponds with a series of dramatic events in the inner solar system. Asteroid bombardment rose dramatically around 3.8 billion years ago, during a period known as the Late Heavy Bombardment. Multiple impacts could have stripped away Mars' atmosphere, while also bringing water and organic compounds that sparked life in some impact craters on Mars. Show odd traits that do not correspond to conventional asteroid crashes. Circular formations with elevated rims and central peaks appear in groups, indicating coordinated hits rather than random bombardment. Alternative explanations involve volcanoes or tectonic processes. However, the crater patterns are not consistent with these natural phenomena. The erosion of Mars' magnetic field is still poorly understood. Planetary magnetic fields require a molten metallic source with active circulation patterns. Mars appears to have unexpectedly lost its magnetic field some 4 billion years ago, leaving the planet vulnerable to solar wind erosion, which steadily took away its atmosphere. However, natural processes do not always cause rapid magnetic field loss. The Earth's magnetic field has reversed several times throughout geological history without causing lasting air loss. The quick removal of Mars' magnetic shield indicates either catastrophic core cooling or external meddling that disturbed the planet's interior dynamics. If intelligent life did evolve on ancient Mars, their fate teaches us important lessons about planetary survival. Even evolved civilizations may find themselves helpless in the face of global environmental collapse or other catastrophic occurrences beyond their control. The red planet may not represent a failed world, but rather a cosmic crime scene with traces of intelligence that was unable to save itself. The search for life on Mars continues, but we may be looking for the wrong types of evidence in the wrong areas. Before becoming a hellscape hot enough to melt lead, Venus may have been the most beautiful planet in the solar system. For over 2 billion years, Venus most certainly had oceans, mild temperatures, and atmospheric conditions conducive to not only life, but also great civilizations that thrived in a paradise. We can hardly imagine. Computer climate simulations reveal the ancient Venus probably had liquid water oceans till 700 million years ago. During this time, the planet received approximately 70% more solar energy than Earth. Yet a thicker atmosphere and worldwide cloud cover may have deflected enough sunlight to keep temperatures acceptable for life. Ocean currents would have carried heat around the world. The planet's extremely slow rotation helps to create stable climate zones. Taking 243 Earth days to complete a single spin might have resulted in distinct weather patterns. Unlike anything else on Earth, huge air circulation cells would have carried heat from the day side to the night side, preventing dramatic temperature variations. This could have resulted in broad temperate zones where liquid water remained steady for millions of years. The lack of a huge moon meant no significant tides, but the planet's dense atmosphere would have produced tremendous wind patterns capable of driving chemical cycles and distributing energy. Atmospheric tides generated by solar heating could have given consistent energy sources for emerging life forms. During this time, the planet's volcanic activity would have produced vital minerals and ingredients for life, while also emitting water vapor and carbon dioxide, which contributed to greenhouse warming. Unlike the cataclysmic volcanism that ultimately destroyed Venus' habitability, early volcanic activity appears to have been more modest, allowing for stable environmental conditions. Space probes have recently identified phosphine gas in Venus' upper atmosphere on Earth. Phosphine is typically created by biological activities, though geological sources do exist. The observed amounts on Venus exceed what known non-biological processes could create. implying that microbial life may still exist in the planet's acid clouds. However, the phosphine finding raises intriguing issues regarding Venus' biological history. What kind of life would have thrived if simple bacteria could survive in the planet's current, harsh upper atmosphere? When Venus had oceans and moderate surface temperatures, advanced ecosystems could have emerged. During the planet's billions of years of habitability, the transition from paradise to hell occurred very fast in geological time. Runaway greenhouse warming caused by volcanic outgassing gradually raised surface temperatures until the oceans boiled away entirely. Solar radiation broke down water vapor in the upper atmosphere, allowing hydrogen to escape into space while oxygen reacted with surface minerals. This runaway greenhouse process could have taken thousands or millions of years to complete, giving any existing civilizations time to realize the hazard and devise solutions. Advanced species may have attempted geoengineering initiatives to reflect sunlight, eliminate atmospheric CO2, or migrate to orbital habitats. Venus' geological record may yet contain evidence of such attempts, concealed behind the planet's thick atmosphere and severe surface temperatures, as well as peculiar mineral distributions. Artificial structures or technological artifacts may be maintained beneath the planet's very young surface, which appears to have been entirely resurfaced by volcanic activity during the last 500 million years. The Soviet Vera landers that successfully landed on Venus in the 1970s and 1980s. The sent photographs showed flat landscapes covered in volcanic rocks, but the harsh conditions limited the mission duration to less than 2 hours, affording only fleeting glimpses of the planet's surface features. Future expeditions with better heat-resistant electronics may disclose more about Venus' hidden history. Subsurface digging may find layers containing evidence from the planet's habitable history. Radar mapping from orbit has already detected unique surface characteristics that do not correspond to normal volcanic structures. If Venus formerly supported great civilizations, their annihilation serves as a clear warning about the consequences of unchecked climate change. Even technology species may be powerless to prevent global environmental disaster. The Paradise Planet became a cautionary tale written in sulfuric acid and molten rock. 2.4 billion years ago, Earth's atmosphere became contaminated with a lethal poison, killing almost all life on the planet. Oxygen, today required for sophisticated life, was once a poisonous waste product that caused the first mass extinction event. However, certain creatures not only survived the catastrophe, but also learned to use the poison as an energy source, possibly developing the first primitive technologies prior to the Great Oxidation Event. The Earth's atmosphere contains almost no free oxygen. Early life forms were anaerobic bacteria that flourished in waters rich in iron and sulfur compounds. These ancient ecosystems were immensely diversified, with species that could get their energy from sunshine, chemicals, and even radioactive decay. Then cyanobacteria evolved photosynthesis and began releasing oxygen into the atmosphere as a byproduct of these ancient microorganisms. Oxygen was simply chemical waste to be discarded, but for most other life forms, it was a corrosive poison that destroyed cellular machinery and caused fatal chemical reactions. The change took hundreds of millions of years, but the results were disastrous. Oxygen levels increased from almost nothing to approaching current levels. The gas reacted with dissolved iron in the seawater, creating vast iron oxide deposits, which we still mine today. Methane, which had previously contributed to global warming, was oxidized and eliminated. During severe ice ages, most anaerobic species became extinct. Some, however, survived by withdrawing to oxygen-free places, such as deep underground or isolated chemical conditions. Others developed sophisticated molecular systems to counteract oxygen's damaging effects. Several species learned to use oxygen as a potent energy source, giving them a significant advantage over their anaerobic competitors. These oxygen-breathing survivors became the progenitors of all sophisticated life on Earth. However, the transition period could have seen more than simply biochemical evolution. Some animals may have created primitive technology to assist them survive in the changing environment. Consider the obstacles confronting clever anaerobic organisms. During the Great Oxidation Event, They needed to identify or create oxygen-free zones. As the environment became more poisonous, they needed new energy sources. As typical chemical cycles failed, they had to devise safeguards against corrosive air gases. Some bacterial species now have impressive engineering abilities that could be scaled up to technological levels. Magnetotactic bacteria make small internal compasses out of finely made magnetite crystals, while other species create intricate mineral structures with features that approach contemporary material science. Biofilm-forming bacteria coordinate their activity across extensive networks that act as primitive computer systems. Ancient creatures facing extinction danger may have developed collective reactions. This approximated technological solutions. The coordinated building of underground refuge systems could have shielded communities from atmospheric oxygen. Selective breeding techniques may have sped evolution towards oxygen tolerance. Primitive metallurgy could have manufactured materials. Oxidation resistance. The fossil record from this period is limited since most species were minuscule and did not survive well. However, some geological formations show evidence of large-scale coordinated biological activity that goes beyond what simple bacterial colonies generally create. Massive strite reefs exist at this epoch, indicating that species were constructing complex structures. Isotope fingerprints in rocks from the Great Oxidation Event exhibit odd patterns that may not correspond to completely natural processes, indicating potential for resource concentration or conservation. Carbon ratios indicate that large organic matter decomposition happened in controlled circumstances rather than random environmental degradation. Some experts suggest that these characteristics imply rudimentary agriculture or waste management systems. The survivors of the Great Oxidation Event gave rise to all complex life on Earth, but they may not have been the first sentient species to endure a global environmental calamity. Their effectiveness in managing this catastrophe may have required collective knowledge and technological capacities for which we are only now beginning to learn the lessons of the Great Dying. Remain relevant now as humanity confronts its own global environmental challenges. The secret to survival could be to learn from the species that successfully adapted to Earth's first major environmental shift. Whether that adaptation was entirely biological or contained technological features may influence how we understand our own odds of long-term survival. 540 million years ago, complex life forms arose unexpectedly on Earth, with a diversity and sophistication that defied evolutionary timelines. The Cambrian explosion produced organisms with advanced eyes, sophisticated hunting techniques, and defensive systems that appeared to have been developed by intelligence rather than by natural selection over time. Recent discoveries show that this evolutionary surge may have been guided by unseen architects prior to the Cambrian period. Life was primarily composed of simple microbes, primitive algae, and simple multicellular creatures that hardly moved or interacted with their surroundings. The fossil record indicates little change over billions of years. Then, in a geological instant, complex species appeared all over the Earth, with traits that should have evolved over millions of years. Trilobites appeared. Compound eyes contained hundreds of properly aligned calcite lenses, allowing for sophisticated viewing capabilities. Modern arthropods evolved similar visual systems over millions of years through progressive refinements. The mathematical precision necessary to construct functional compound eyes reveals technical principles, not random evolutionary experimentation. Anomalcaris, one of the Cambrian's top predators, has flexible grabbing arms. With advanced hydraulic mechanisms for grabbing prey, its body design combined traits from several animal groups that would not emerge together again for millions of years. The creature's adaptations appear almost artificially built. Rather than spontaneously evolving, hallucinogens walked on numerous pairs of spiny legs and defended themselves with rows of defensive spikes. This unusual anatomy on its back provided distinct practical objectives. However, precise coordination between numerous organ systems is essential, as is the possibility of such complex integrated traits arising simultaneously using random mutation procedures. Zero. Even more puzzling. Many Cambrian species possessed characteristics that provided no discernible survival advantage in their old habitats. Some organisms have sensory organs designed to detect substances that were not present in substantial amounts during the Cambrian period. Others created defensive constructions that were optimized against predation techniques. There were no known predators employed at the time. These anticipatory adaptations indicate that organisms were developing responses to future environmental situations or threats that had not yet emerged. Natural selection can only respond to existing selective pressures, not future difficulties that have yet to emerge. The occurrence of apparent premature adaptations suggests a sort of controlled evolution, guided by AI capable of foreseeing future ecological changes. Another Cambrian-era oddity has been discovered through genetic examination of current species. Most main animal body designs and developmental genetic toolkits appeared at the same time during this brief evolutionary window. The sophisticated genetic machinery needed to develop eyes, brains, and limbs appears to have been invented all at once. Rather of being progressively formed over millions of years, the hawk genes, which control body plan development in all complex creatures, reveal evidence of quick coordinated modifications during the Cambrian period. These master control genes influence the expression of hundreds of other genes and shape essential features of animal architecture. Changes in numerous HOK genes might theoretically be directed by external genetic engineering. Some researchers hypothesized that horizontal gene transfer between species may have expedited Cambrian evolution. Bacteria constantly exchange genetic material, allowing favorable mutations to spread rapidly throughout populations. If early sophisticated organisms were capable of horizontal gene transfer, evolutionary breakthroughs could have been shared among species rather than arising individually. However, horizontal gene transfer necessitates specialized molecular machinery to incorporate foreign DNA without disturbing critical cellular processes. The accuracy required to correctly incorporate complex genetic alterations points to advanced biotechnology rather than natural bacterial processes. Alternative interpretations point to environmental changes that resulted in new selective pressures during the Cambrian epoch. Rising oxygen concentrations alter ocean chemistry and predator-prey. Arms races may have spurred evolutionary innovation, but the rate and coordination of changes still outperformed what these environmental circumstances should have produced. The Cambrian explosion could be proof of the earliest biological engineering endeavor on Earth, guided by emerging creatures' intelligence or unknown external forces. This evolutionary burst indicates that complex life can be controlled and sped far beyond natural rates. The builders of the Cambrian explosion left their mark in the genes of every sophisticated organism on the planet, which are lodged in millions of year-old rocks. Strange items reveal incredible stories about the Earth's ancient past. These out-of-place artifacts, which conventional science dismisses as hoaxes or misidentifications, continue to emerge from coal mines, quarries, and archaeological sites worldwide. While the majority can be explained by natural processes or contamination, a few are truly perplexing and challenge our concept of geological time. In 1844, Scottish physicist Sir David Brewster reported discovering a metal nail lodged in sandstone from a quarry near Glasgow. The rock formation was around 400 million years old, long before complex life evolved on land. Chemical research indicated that the nail was made of iron with traces of nickel, consistent with manufactured metal, not raw iron ore. Similar finds include a 300 million year old gold chain discovered inside coal. A bell-shaped vessel was recovered from solid rock in Massachusetts, as well as many metal spheres from Precambrian deposits in South Africa. Each finding has the same pattern: manufactured objects discovered in geological environments that predate human civilization by hundreds of million years. Skeptics accurately point out that most reported out-of-place artifacts can be attributed to contamination, misidentification, or fraud. Modern things can enter old rock via fissures, root pathways, or human disturbance. Natural minerals can take on shapes similar to artificial things. Hoaxsters are motivated to fabricate phony findings that generate exposure and prospective cash rewards. However, a few situations are difficult to debunk. The Wolf of Iron, unearthed in Austria in 1885, is one of the most well-documented unusual objects. The cube-shaped object was discovered lodged in brown coal, going back 20 million years. Multiple expert investigations validated the artifact's artificial origin while ruling out natural formation processes. The relic weighs 1.73 pounds. Each side measures around 2.6 inches. Deep grooves cut into its surface form, resulting in exact geometric designs that do not occur naturally. X-ray investigation indicates an interior structure that is compatible with cast metal manufacture. Carbon dating of the nearby coals supports the deposit's ancient antiquity, which is particularly noteworthy. The object's makeup contains materials that do not naturally occur together. The core metal looks to be iron, but it contains strange trace elements in amounts that indicate artificial alloy manufacture. No known geological mechanism could produce this particular mix of metals in the given ratios. The Antikythera mechanism, while not embedded in ancient rock, reveals how advanced technology may be lost and forgotten over thousands of years. This ancient Greek contraption had bronze gear mechanisms clever enough to calculate planetary locations and predict eclipses. Its discovery in 1901 transformed our knowledge of ancient technological capabilities. If Greeks could create mechanical computers 2,000 years ago, what technology would civilizations have developed over the planet's 4 billion-year history of life? Under some conditions, the fossilization process preserves only tiny fractions of ancient creatures. Technological objects would have a far lower chance of survival. Geological processes recycle most surface materials over millions of years. Modern industrial archaeology shows how rapidly technical evidence fades. Abandoned industries rust away. Within decades, electrical gadgets degrade into unrecognizable bits. Even large concrete constructions crack and crumble when subjected to natural weathering. However, certain materials have the potential to live for millions of years under ideal conditions. Metallic glass retains its structure longer than normal metals. Some ceramics withstand chemical disintegration throughout geological time periods. Crystalline materials have the ability to preserve microscopic characteristics over long periods of time. The search for old technology relics presents basic obstacles. We don't know what materials previous civilizations employed or what their technologies might look like after millions of years of evolution, according to archaeological methodologies.